So in the morning, about the books, often sounds reasonable, except that it may not have all the practice questions. And the way we discussed that you can pick Shom series, the one which is on the random variable and stochastic processes for doing some problems. Any good book on quantum mechanics that should also be having questions on finding out the expectation values, finding out the variances on the basis of the PMFs and the PDFs, except that the word probability density function doesn't come that often. What we use in quantum mechanics is the word wave function, and then we build probability density function from the wave function. So psi star psi or mod psi square, what the way you call it. And after that, everything what we are doing in probability statistics basically follow. That means that PDF should be a properly normalized PDF. It should be integrated to 1 to give the normalization constant. Then you can find out the expectation values. Then you can find out the variances, so on and so forth. So I will do a question today, although it is possible that some of you might have already attempted it in your BSc, but I will still do it just to give you an idea. Okay, so what I wanted to do first, but at least I wanted to have one continuous variable, continuous random variable distribution, and the simplest among it is uniform. So I will test this uniform distribution, and then I will do this problem, and then tomorrow we will continue to build on these things. Okay, so when I'm talking about a uniform random variable and I want to write down Px. So at this point of time, I'm not even telling you what are the parameters, but I'm just asking a question. What comes to your mind when I say that there is a uniform random variable? Uniform. Okay, let me rephrase then the question. If I want to plot probability as the function of x, and let's say that a random variable is uniform between a to b, then what do you think it means that there exists a uniform random variable between a and b? What happens to the probability?
So we'll get a probability density instead of getting a mass function.
Yeah, it is PDF, right? Absolutely fine. But what kind of PDF we are talking about? See, we are trying
Sir,
to
I think it
understand.
is horizontal line, so probability will be same.
So what it means, absolutely right, that if I choose an interval and if I choose the same width interval anywhere else, then the probability value should remain same, or in principle what should be there, that it's a constant probability between 2 points A and B. So it is something like Px is equal to, let's say, a constant, say a k, between a less than x less than b, and it is 0 otherwise. So this PDF is the simplest of the continuous random variable. It's basically a constant. Now certain questions come to mind. One, are there any parameters in this PDF? Two, how to find k? So these are the two things which I am thinking of. Are there any parameters in this distribution? Random variable, sure, x, and this random variable takes continuous value between a and b and 0 otherwise. So of course anywhere else if you think about the value, that will be 0. So this value will remain 0 everywhere else. Now in order to understand it, let's just first do something which is trivial, which you guys have been doing. Find out the normalization coefficient k. So how to find k?
Take integral of px dx equals to 1.
Very good. So a to b px dx equal to 1. So what will be this? So k is a constant. You can take out a to b dx is equal to 1. So what is k?
1 by b minus a.
1 over b minus a. Right. So your px becomes 1 over b minus a for this interval a less than x less than b and 0 otherwise. Now, can you tell me the parameters which are involved in this distribution? What values I have to give you a priori so that you can write down the PDF?
So is it the two endpoints?
A
Right.
and b.
A and B, absolutely right. So please see that the uniform distribution, even though the name suggests that it looks very simple, and it is very simple, but as soon as I write the PDF in the form 1 over b minus a, it's independent of x, fine, but this PDF will have no meaning unless I specify a and b. So if I say that there is a uniform random variable, it will mean anything only if I tell you it is uniform in the interval a to b. So this a, for example, if I say there exists a uniform random variable in the interval 0 1, what will be PDF
1.
px for that? So this
1.
guy px will become 1 between 0 to x less than 1, and this guy plays a very important role in the generation of random numbers. In any Monte Carlo analysis where we deal with the random number generations, this uniform random variable, which is nothing but px equal to 1, plays a very important role. In fact, you find out that we can generate PDF of any arbitrary distribution once we have the knowledge how to generate it for px equal to 1. Most of the programming languages have an inbuilt function to generate uniform random variable between a to b or 0 to 1 things. So uniform random variable, this guy is very useful in the case of Monte Carlos. And I doubt, I mean, since you are not doing anything with the Monte Carlo at present, so let's not talk about it for the time being. But otherwise also, we can think about a particle passing through some detector system saying that on an average, particle is losing its energy constant in the constant manner. It means that while traversing the distance between the endpoints of the detector system, particle is losing energy which is constant in any of the interval. So at times this is one of the simplest approximation for this particle passing through something. In fact, this turns out to be the first portion whenever we are going to do any particle measurements in the detector system. Everything else, for example, a charged particle losing energy in the form of famous Bragg's peak or the Bethe block curve, those all come later on once we understand how the particles behave if they lose energy in a constant manner. So dE by dx, for example, remains constant. Something like this. So we use uniform distributions in variety of places. One place is of course Monte Carlo simulation, which at this point of time you are not doing, but those who will be taking advanced numerical techniques course or once we go to the research level, I'm sure that you are going to use it. Of other places, uniform random variable, wherever you find that the anything is distributed in a constant manner, that's the place where the uniform distribution is used. Okay, so this is about it. By the way, if you have to plot the uniform distribution, it's not done in the manner that you will be able to plot the PDF at every point. You are always going to divide certain intervals, and in each of the interval you are just going to find out the frequencies And that's how you plot any continuous random variable. You cannot plot it at each point, so you subdivide those points in the intervals, and in those intervals you plot it. So those guys who will be plotting Gaussian distribution, for example, for the counting statistics, they will be doing this thing pretty often, but that we will talk about when we will come to Gaussian. So what are the things which we can do in the continuous random variable? Again, the same things. I can ask you to find out expectation value of the random variable, the variance of the random variable, so on and so forth. So let's just try to find out the expectation value. This is the simplest one, so it doesn't take that much of the time. So how to find out? In this case, it is x dx dx integral between a and b. So what will be the result then?
A plus B by 2.
Oh, that was pretty fast. So Px is 1 over b minus a, and then I'm sure what you have done is x square over 2, which is the integral of x, and then you have simplified it, b square minus a square over 2b minus a, expanding your b square minus a square and b minus a and b plus a, you are done with this b plus a over 2, and this is right. This is actually what basically, I mean, if you think about it in terms of intuitive one, if I ask you what is the average point in a PDF which is constant, you will see, sir, it should be a midpoint. I mean, that should be an average. Okay, so this is not visible here. So it should, of course, lie somewhere here, exactly at the center. And this is nothing but a plus b over 2. So that's intuitively also there. But is there a variance in that? If so, what is the value of that? That's not very common to think of. That what is the spread in the value around this mean? So here, of course, the probability laws come into the picture. You can figure out, I would say, do it in the manner of ex square minus ex whole square. You have already found expectation value of x, which is nothing but the mean in the case of constant PDF. So find out expectation value of x square exactly in the manner in which we found the mean, and give me the result. So expectation value of x square. Is what? B cube minus a cube over b minus a times 3, right? So you will have to think about expanding b cube minus a cube now in terms of b minus a, so that factorize it.
Sir, b minus a,
Okay.
b plus a plus ab.
B plus a plus ab
B square
time
plus a square. Sorry.
mix. Yeah, right. That makes sense. B minus a over 3 b minus a. So b minus a cancels. Whatever is left is ex square. So what will be variance? Which is ex square minus e of x whole square.
Sir, is it a minus b whole square divided by 12?
So is it b minus a
A
whole square divided by 12? Okay,
divided.
let me see if others also
Yes,
get the
sir.
same answer. B square
Yes,
plus
sir.
a.
It's correct.
Okay,
Yes, sir.
3 minus, okay, let's just do b plus a square over 4, and you should get this guy, which is absolutely right. And then I can write down standard deviation, which is a rather common one, b minus a, it has to be a positive one, over root 12. So if you want to write something similar to what you wrote in the case of Poisson distribution, you will see that A plus B over 2 is the mean, and the spread around the mean is given by B minus A over root 12. You may find it interesting that, okay, I mean, I started doing my research on silicon detectors. And what happened that we were supposed to find out the energy loss in the silicon detector. I mean, silicon detector, just like any detector, will have the particle passing through it and it detects it. Okay, and we were studying a research paper. So somehow that research paper simply wrote that while the particle passes through it, of course, B minus A was nothing but the depth of the detector, and then it writes that there will be, in that case, that the width of this is given by D over root 12, where D was some distance there. And we got confused. I mean, to be honest, I was reading a research paper and I thought, from where this did this guy wrote D over root 12? We didn't even think about it, that it was the simplest assumption which this author was taking, that the particle is passing and losing its energy uniformly over the whole detector. And it took us some time, and while after discussing with our supervisor, to figure out that this D over root 12 term comes from the uniform distribution. In fact, this root 12 in the denominator is the characteristic. Whenever you find out that the width is given in terms of this root 12, you may please try to correlate with the simplest distribution is applied in the case, which is nothing but the uniform distribution. So in the uniform distribution, I mean, we can find out, of course, all the other things, just like the way these two I mean, you have solved these two integrals. You can solve it for the skewness, you can solve it for the kurtosis, so on and so forth. Basically, we do need to figure out that the distribution, once the idea is, once the PDF is given to you, everything related with the distribution is given to you. Hence, you can find out all the important quantities related with it. And there lies the question which I wanted to give you, something which I am expecting that you have done it, but I still wanted to do it since this additional class is mainly about solving problems. So a position wave function is given to you of the form ne minus alpha x square, where n and alpha are both greater than 0 and x, one dimensional variable, lying between minus infinity to infinity. And what I am interested in finding out, see, I am interested in finding out, of course, n to begin with. Then I'm interested in finding out something what we call as the average position, which is nothing but the expectation value of the random variable x, where x is sort of position, not sort of, it's a position, or in our language, the way we are writing is this. Then we are interested in finding out something what we call as sigma x square, which is defined as, again, the variance, this, or in our terminology, ex square minus expectation. Okay, let's not stop here. Find out momentum operator. So let's me just tell that this is nothing but the operator, finding out something like this in quantum mechanics books, what you are finding out. And next, you may be asked to find out sigma p square, which is something similar to what we are doing here. So let's write down in the manner in which we are writing out E of p square minus this guy. And finally, check for this, what is the value you are getting for sigma x, sigma p, which is nothing but at times the uncertainties. In quantum mechanics book, sometimes you will find out this guy is written as delta x square, and this guy sigma p is written as delta p square, so that you are finding out delta x times delta p. But this is just the nomenclature. The question is coming directly from the probability and statistics knowledge. All we are supposed to do that because the sigma x, sigma p hold is special interest, right? In quantum mechanics. What is this sigma x, sigma p values? I mean, in general, from where do you get it?
The uncertainty principle.
Uncertainty principle.
Right. So what does uncertainty principle say something about sigma x and sigma p?
Their product should be greater than equal to h bar by 2.
Right. So their product should be greater than. So at times this question comes in the manner that if this wave function consistent with the uncertainty principle, or whether this qualifies to be a reasonable wave function, because if it has to be a physically realizable situation, then the uncertainty principle should hold true. So sigma x times sigma p should turn out to be at least equal to h cross 2. Other times these questions are useful because see that there exists greater than equal to sign. So you are always interested in finding something, a wave function which will have this equality sign holds true, because this is the minimum value which can be ascribed to sigma x and sigma p. So out of various possible wave functions, the one which assigns the minimum value to sigma x times sigma p is the one which at times you would like to use. So there are several reasons for doing it. But this is again coming directly from the quantum mechanics. And here I will make your life a little bit easy, although you can find out the integral. So I will give you this e minus ax square dx. You can of course use your knowledge of gamma function by writing ax square is equal to y and do this problem. But I am giving you this integral pi over a. And not only that, I am also giving you another integral minus infinity to infinity x square e raised to power minus ax square dx. This can be done by, this is equal to 1 over 2a root pi over a. By the way, once the first integral is given, I need not to give the second integral, because if you differentiate the first integral on both the sides and change the order of differentiation and integration with respect to a, so you will find out that you will be able to get the second integral just by taking the differentiation with respect to a for the first one. So d by dA of exponential minus ax square will give you term of the type x square times exponential minus ax square. And then rearrange, of course, differentiating on the right hand side and rearranging the terms, you should be able to get this. But anyway, I mean, these two integrals are given to you. So let's just solve it in this class. So find n, the first thing.
So 2
So
alpha
you,
by pi whole to the power
yeah,
1 by 4.
so first I would ask you to write down px just to make sure that we understand it from our probability statistics. And this is psi star psi, which mod n square, I'm sure that you have done this, minus 2 alpha x square. Now, do you see the parameters in this PDF? If so, how many?
Alpha and n.
Alpha.
Okay, right. Is n a parameter? No, n is not a
No, n
parameter
is a
because
n will be
n is a
determinant.
normalization
Yes, sir.
constant, right? So
Alpha.
this PDF, in all probability, you can write down as px alpha. This is just to make sure that we understand that whenever you get a PDF or psi, you understand what are the parameters which are involved, nothing beyond that. So, okay, I mean, let's just do the integral. I mean, this is rather simple and somebody has already done it. So, minus infinity to infinity px dx equal to 1. So, this should be equal to what? Mod n square times what? Pi over 2 alpha equal to 1. And immediately you get your mod n square. 2 alpha over pi half. And generally, I have a habit of keeping mod n square because most of the time the integrals will have n square coming in. Although you can write down your normalization coefficient n, but I'll keep it like this. Fine. So this looks rather simple. Let's just try to find out average value. So please see what is meant by expectation value. As long as you understand it, now it makes all the things rather simple. That when I am writing X operator, this guy means that we are writing psi x psi. That means that the position wave function at a given instant is given by this psi. And when I am trying to find out the expectation value, it just means that there are plenty of such states, all identically made exactly in this psi x, and I am trying to make a position measurement on all of these and taking the average of it. The reason why I say the ensemble word, why I say that they are identically indistinguishable made states together, because by this time we know that an operator after operating on the xi may change the wave function, and hence any new measurement of this operator on the new measurement on the new wave function will result in something totally different. So we are not interested in that. When we are saying that we are trying to find out the expectation value, we are making a position measurement or on identically prepared states. Okay, but that's mainly the physics, and mathematics goes simple, because all you have to do is to do psi star x psi minus infinity to infinity, which in this case will become rather simple, x mod psi square dx from minus infinity to infinity. So what will be this? Minus infinity to infinity x mod n square exponential minus 2 alpha x square dx. And this guy will be?
The 0.
0.
And this is 0 because?
It is an odd function.
Right. Very good. So this is the reason why I did not give you the any other integral, because x time exponential minus 2 alpha x square integrated from minus infinity to infinity will basically have the odd function being integrated in the symmetric interval, and which is going to give you 0. So that makes life easier. Do the same thing for x square, which quickly you can write down mod n square x square e minus 2 alpha x square dx. And I should go back and please look at the formula which I gave to you, 1 over 2a root pi over a. Okay, so waiting for an answer.
So it's 1 by 4 alpha.
1 over 4 alpha, and 3 of you said it, so I will take it right. And that means I can very quickly write down sigma x square, which is
So it is root of 1 over 4 alpha.
wait, okay. This is root 1 over 4 alpha.
Yes, sir.
No, sir, 1 over 4
Why
alpha.
would you
No,
say
sir.
that?
No, sir, 1 over 4 alpha.
Go back to this previous. See, 1 over 2a root pi over a. Now, n square term will take care of this root term. I guess that cancels. and you will be left with something which is as simple as 1 over 2 times A, nothing else. Isn't that happening?
Yes,
And since
sir.
A in our case is
Yes.
2 alpha, so this becomes 1 over 4 alpha. This is, I personally believe, that is how, I mean, the simplest of the thinking will give me 1 over 4 alpha. Right? Because mod n
Yes.
square is there
Yes,
and it
sir.
will take care of this root term.
Yes,
Okay,
sir.
so quantum mechanically, what does this mean? What does this mean when I am writing something like this? What do you say about this particle? So the wave function, can you draw the wave function? If this is, let's say, x equal to 0, and I ask you to draw maybe psi x or px, the only difference will be that it is falling, px will be falling sharper because of this 2 alpha and alpha being greater than 0. Can you draw this? What kind of wave function we are talking about?
It's Gaussian.
It's, it's Gaussian, but what happens to x equal to 0? This guy will be n, some number. This
Yes.
was like this, and okay, very bad drawing, but this guy is something like this. Okay, so I have to have my xi x continuous. It cannot be discontinuous, right? So what do you say about this particle? This particle on an average remains where?
Within a
At
range of
x
1
is
over
equals to
2
0.
root alpha from the center.
Yeah, so okay, I mean, the questions can be asked in terms of probability at different places, but when you are finding out the expectation value of the x, this is something similar to what you have been saying whenever you think about a particle in quantum mechanics, that this guy is at x equal to 0 on an average, but that does not mean that it remains there. The uncertainty in that is given by your sigma x, which is nothing but 1 over 2 root alpha. So this sigma x is given you the uncertainty in that average position. And in all the cases, you may be asked to find out what is the probability that it remains in the small interval between, let's say, minus 1 over 2 root alpha to plus 1 over 2 root alpha, things like those. The particle has this possibility of moving around from minus infinity up to plus infinity. Yeah. Can this alpha be less than 0?
No, sir.
No, will not
And
be
why
able to
not?
normalize.
Right, because we have given you exponential minus 2 alpha x square. So if alpha is less than 0, that means that the exponential term will grow with x. And if that happens, then this will not be true wave function from minus infinity to plus infinity. Okay, so those questions are useful, but okay, I mean, do something similar in the for P. Now, P operator in quantum mechanics, particularly in position representation. So what are you supposed to do? You are supposed to basically find out psi with P operator in position. So it should be minus I h cross minus infinity to infinity psi star d over dx psi. And of course, my psi star x is the form. Psi x is also the form. So please do this and let me know what the result is. So d by dx of exponential minus 2 alpha x square. D by dx of exponential minus 2 alpha x square. This will be minus alpha x exponential minus 2 alpha x square. Right? No, there is something missing.
Yes,
No,
sir.
sir.
सर 2 से मल्टीप्लाई भी होगा.
There is one thing which is missing. Yes. So this should be,
multiplied by 2.
which means that this should be minus.
4.
But is this right? What I am doing?
No, sir. You have to
Oh. So
differentiate
what
with respect to e to power minus alpha x square, not minus
that
2.
so there is already, you can see that this guy should not have been there. D over dx psi x. Psi x was only exponential minus alpha x square, right? So that
Yes,
means in
sir.
the first place I should have written just this. Make sense? Yeah, these are the trivial ones, but this happens while you are doing this final examination problem, and then it, unfortunately, I mean, we have to deduct marks for those things. But yeah, I mean, please take care of this. Now, what will be the average P operator?
0. Sir, 0.
Zero, because you
Yes, sir.
again
0.
got
Odd
this
function.
x
It's an
times
odd function.
exponential minus alpha x square odd function. This will be 0. So the question looks simple in that aspect. But now p square will not turn out to be 0. Simple reason. One, if it has to be a good quantum, I mean wave function, then sigma p times sigma x cannot be 0. Right? I mean, sigma x times sigma p should be greater than equal to h cross over 2. And the second one, that you are going to do the second differentiation and there should be x square term. So it won't be 0. Anyway, please do that.
Sir, alpha h cut square.
Let me just a sec. Alpha h cut square. Okay,
Square.
let me just wait others to also say something.
Yes, sir. Alpha h cut square.
Okay, so what you got for d square over dx square alpha minus x square?
So minus 2 alpha.
Minus 2 alpha
Inside the bracket, we have e to the power minus alpha x square.
minus alpha x square. Okay, I mean, doesn't matter. Let me just write down two terms explicitly.
Then the
Okay,
other one
and
will be 4 alpha square x square
plus or minus?
plus
Plus 4 alpha,
4 square x square
right?
e to the
E
power
to the
minus.
power minus alpha x square.
Okay. So two of you have said that, or maybe two, three. Alpha h cut square. Anybody else? Because then you have to, of course, multiply it by alpha minus alpha x square, which makes it minus twice of those, and then two integrals.
Some minus
Sir,
2 alpha x.
Sir,
minus 2
inside in
x.
front of h bar ka square initially, do we have minus sign? Because iota will cancel the minus sign,
No,
right?
no, there minus I h cross d over dx whole square, right?
Yes, sir.
So this will become what?
Sir,
Minus cancel plus
oh,
I
okay, okay.
square h cross square d square over dx square, right?
Yes, sir.
Yeah, so that should give you minus.
Sir, I'm also getting alpha h bar square.
Okay.
Yes, sir. This.
Okay, this is actually right. Yeah, I mean you should just do this integral, and the whole reason for me giving you this or this kind of problem is just that you get comfortable with your integrals. It doesn't require that much of the concept. I mean, mathematical rigorous portions, but it just requires you to do a basic integration. Yes, at times you are supposed to do this integration by parts, etc., but those cannot be very difficult. Anyway, so you will get this. I agree with that. Okay, alpha h cut square. That means your sigma p square, that will be alpha h cut square, which means your sigma p will be root of alpha times h cross. Now, can you do your sigma x times sigma p? What did we sigma x? What did we get for sigma x? 1 over 2 root alpha. So 1 over 2 root alpha. And what do we get for sigma p? It is root alpha times h cut, which is so interesting. This wave function is an interesting looking wave function, which gives you the minimum uncertainty in x times the sigma p. In fact, Gaussian wave functions, they represent something very important in quantum mechanics. What do they represent? In quantum mechanics, let's just think about it. In quantum mechanics, if you want to represent a particle by a wave of the kind EIKX, what's the problem in that? So this is a plane wave. Now, if you think about the particle association, then K is nothing but related with momentum. So H cross K is momentum. So this wave defines a definite momentum wave. What problem do we face in this? If I want to represent a particle by this?
Sir, it's not localized, the particle.
Yeah, not only that it is not localized, your sigma p will turn out to be 0, which means any sigma p sigma x greater than h cross by 2 you cannot build. If you want to normalize this kind of a wave function, plane wave function eikx from minus infinity to infinity, you will get the result which is infinity. That means all non-normalizable wave function. Uncertainty sigma x greater than h cross 2 over sigma p means what? For a definite momentum particle will be greater than infinity, which means what? That the particle, that's the way you said it, the particle is not localized. So what do we do in quantum mechanics to get a localized particle?
So we take superposition of these plane waves.
So we take EIKX, and since K is not limited to discrete values, so you have to have some sort of a decay and some function, this function of AK or AKX I can write down. And then you integrate. This is the famous Fourier transform technique which you do. Which is the commonest AK function which you use there. The one which you use is the Gaussian one, and the reason for using Gaussian one is actually shown on the previous page, that the uncertainty for this Gaussian is the minimum uncertainty which you can build. There are plenty of other good things about the Gaussian wave function, but a particle is represented by what we call as wave packet in quantum mechanics, which is nothing when you are saying the superposition over several decays appropriately weighted with some function. And the commonest wave function is the Gaussian wave function. There are some other things about the Fourier transforms of the Gaussians, which I will try to highlight while doing the Fourier transform when we will reach to that after doing the complex integration. So I'll mention that, but please remember this thing. In quantum mechanics, you do not represent particle just by a plane wave. A particle does not remain localized. Particle in that EIKX is not normalizable in position, so you cannot use it. So this is what you build in your quantum mechanics, a particle which is nothing but the superposition of certain case. As soon as you are doing this superposition, what you are doing, your sigma p, the uncertainty in the momentum, will no longer be equal to 0, because you are building wave functions of different k's. So that means one of the k value will be maybe there as an average one, but it will have some uncertainty and then appropriately weighted with this function. So please remember that this is important aspect of the quantum mechanics, and that is why it is very difficult to even deal with the plane waves in quantum mechanics. Even though we use it very regularly, but representing a particle by a plane wave, that is a difficult one. Okay, what about this? If I give you psi xt, the same wave function, but now I am also putting the time dependence e I omega t. So I just put this, which is no longer, now I'm not talking about just the stationary state, I am giving the time evolution. What difference will it make to the problem which you have done? So what problem have we done? We have done a problem in which we found n, we found expectation value of x, we found expectation value of p, so on and so forth. So what difference it is going to make into our result sigma x times sigma p?
So it will be same.
And
Yes, sir. It should
why?
not change because
Suppose the iota part will have the complex conjugate and it will get cancelled out during the integration.
Psi star psi, this is what you are saying, sir, will still be mod n square e minus 2 alpha x square. And wherever, since in all these cases we are just building that, so e I omega t will cancel out with e minus I omega t, and it is not going to make any difference, which means what will be the time evolution of this? The time evolution of this kind of wave is not going to be affected in terms of, let's say if the particle is localized, then that particle remains localized at all possible times, even if the wave function is this e I omega t. In fact, if you are looking into it, every time I am using my result, I'm using mod n square. Now think about this also, since we are saying something about the quantum mechanics. So we got mod n square 2 alpha over pi root. So let me just write down 2 alpha over pi. This is this. Now if I want to write down n, what will be that? So you will say quickly, sir, it will be
1 by
2
4th of
alpha over pi 1/4. But
yes.
please remember that this thing will hold true as long as my n remains a real number. In fact, I could have done any of this 2 alpha over pi 1/4 times e I theta, and that is a valid n. You multiply n star n, you will still get the same mod n square. Yeah. So even though the quantum mechanics which we are doing at present is not affected by a choice of ei theta, and it is common to choose theta is equal to 0, which means ei 0 is nothing but 1, and we use this normalization constant. But please keep in mind that the normalization constant is fixed only to an arbitrary phase factor by this normalization condition. We have a habit of saying that we fix the normal by fixing this normalization coefficient. I mean, by taking this total probability to be 1, we can fix this n, but this n fixing to real number has to be something which we impose. Otherwise, it will remain true, n is equal to 2 alpha over pi 1 over 4 with a phase vector ei theta, and it will still give all the possible results. And there is nothing which will be changed in our overall treatment of this. However, in certain problems related with quantum mechanics, this freedom of choosing this phase factor of I theta, this freedom becomes rather relevant. And I am not telling you right now, but when you are going to do the QM2, you are going to do the relativistic quantum mechanics, and those of you who may go for field theory will see the importance of that. So if the phases don't change anything in terms of the result, what is the purpose of the phases then? If the phase don't change anything, I mean, the results remain same, n star n. What's the purpose of phase? Same question which I asked. I mean,
Sir, if
sometime. Yeah, please go ahead.
sir, if phase is different, then of course the resultant will be zero. It will gonna affect the superposition.
No, I mean the phase. See, ei theta. This phase factor is there in this normalization coefficient. But whether you put it or whether you do not put it, all the results which you have got for sigma x, sigma p, they will hold true. Yeah.
So just a guess, can it help in something related to degeneracy?
What kind of degeneracy? I mean, degeneracy word generally means that we are talking about having the same states.
Yes, sir.
Two different states having same values of eigenvalues, maybe say energy or something else, right?
Yes, sir.
Yeah, but
So
I
in
would
that case,
suggest
it can
that
help
yeah, I mean,
in
what you are
differentiating
trying to
the
say
two
is
wave
that
functions.
by choosing different phase factors, you can try to make two states which look otherwise similar uh, different. Yeah, I mean,
Yes,
otherwise
sir.
similar means
Yes,
they are
sir.
degenerate. But whenever you are actually facing a problem of evaluating anything, you will still face this major issue that you will have the phase factors cancelled out, and hence any measurement which you are going to do, your measurement will still give the same result. You see the problem, I mean, that way. Even though you choose a different phase for one state as opposed to another one, but any measurement which you are going to make on that system, since that measurement is going to have this n star n kind of thing or psi star psi kind of thing, so those
Yes, sir.
phase
Got it.
factors will ultimately go. Yeah, but please remember, this is something which you have learned from double slit experiment. And what was that?
Superposition of two wave functions.
Right, right. Whenever you are going to do this psi 1 plus psi 2, this is the famous linear algebra, or C1 psi 1 plus C2 psi 2. If your one wave function is a simple psi 1 or another one is C2 psi 2 times ei theta, now you take mod psi 1 square or a square or mod psi b square. Will you get the same result or not? So the superposition principle, will this mod psi a square will be same as psi b? Because all I have done, I am saying that psi 2 is replaced by psi 2 prime, and both of which are related by a phase factor. So psi 2 prime is nothing but psi 2 times ei theta, where theta is not 0, let's say. Will that mod, I mean, okay, the way I am writing it is should be this guy square and this guy square. Will these two give this identical results? Tell me. So think about that.
No, sir.
Sir, if the phase is same, then it will give the same result.
No, I mean theta
Or
is 0,
else
then there
theta
is
is
the
0, then it will
possibility.
give. Otherwise, it will depend on theta.
It will depend on theta. So it may not be. It is true that the absolute phases don't count, but the relative phases do. Remember, this is the important point which I did mention a little bit about while I started with my lectures on linear algebra, that phase factors even though in the absolute sense don't seem to contribute much, but phase factors can be very useful in understanding wave related results. Particularly the double slit experiment, for example, cannot be explained unless until we have these phase factors built in. Why our psi needs to be complex, why the phase factors have to be there. So these are important points. There is one more thing which I wanted to tell you. This is something related with the normalization, and now that I'm saying it, I should do that. So it's a common way to write, for example, n e minus r a naught. This is a famous psi1s wave function. Normalization coefficient exponential minus r over a naught, where this is generally written in spherical polar coordinates, and a naught is your famous Bohr radius. Please see that when generally it is written this, it means that we are giving you r theta and phi, which is equal to ne minus r a naught. This guy, when you try to convert it into probability, psi star 1s psi 1s d cube r, or the volume element which one has to think about, which is nothing but r square dr sine theta d theta d phi. So this is the three-dimensional spherical polar coordinates which are used. So do your, I mean, whenever a problem like this comes and if you are not clear what is asked, then either make yourself clear. Otherwise, you will have problem of normalizing this guy. I mean, everything else, if you do not use r square, will start making some different okay, implications. So psi1 is star psi1 d cube r is what you are supposed to take care of. So this becomes mod of n square, where r is going for, I mean, the regular ones which you know of, exponential minus 2r over a naught, and then this r square term dr sine theta d theta d phi. Do you know what are the integrals for r theta and phi? Can somebody tell me?
So phi will
Spherical
give a
polar
2 pi.
coordinates. Phi will give 2 pi. Okay. This is from 0 to 2 pi. What about sine theta d theta?
0 to pi.
0 to pi.
0 to pi.
So 0 to pi it
Sir,
gives
2.
what?
2.
2.
It gives 2.
2. So you get something like 4 pi mod n square r going from 0 to infinity and not minus infinity to infinity, e minus 2r over a naught r square dr. So there is one r square term which is already built in this psi star psi normalized to 1. So this volume element, please do not neglect it. I see that we actually gave a problem once, and few students, not all, not of course all, but they did not take care of this r square dr, even though they used this reasonable r greater than equal to 0, which means they integrated from 0 to infinity. Still they had this r square factor not being factorized there. And of course, we did not give 0, but that unnecessarily we had to deduct marks for these things. So be very clear what is actually given when the wave function is given to you. Is it a three-dimensional, one-dimensional, or what? Had it been generally in the two-dimensional coordinate, it is the area element which is given, right? And then correspondingly you will have to think about the area element dA, which can be dx times dy, or in the polar coordinates can be a simple, again, r dr times d theta. You'll have to correspondingly integrate. And this is also making one thing interesting. Does psi have units or not?
Yes, sir.
So what's the unit which we ascribe to psi?
N upon volume units.
So in this
Sir,
case, right, go ahead, say it.
सर वॉल्यूम एलिमेंट का स्क्वायर रूट।
Right, absolutely right. So please remember that the way we think about probability density Px dx, since Px dx gives the probability, so Px and dx should have inverse relation in terms of the unit. So whatever be the unit of dx, px should be 1 of over that, so that we can actually get the probability, okay, term probability dx. So this is the implication of using PDF and the reason for using the word density, that this px is no longer dimensionless. I mean, as long as your dx have dimension, in the position wave function, since we use psi x, okay, psi star x, psi x dx to be the probability. So psi x should have the dimension which is whatever the dimension of dx, and in the case of position, of course, it is x, and you will just put position there 1 over root. On the other hand, if we start talking about phi star p, the momentum is space, dp, then correspondingly, the wave function in the momentum space, if we are talking about those, the corresponding units will come from the dp, or wherever in the continuous random variable we are using this PDF. Please ensure that you understand what is the volume element, the length element, or the area element. In the problem which I have given for the hydrogen atom, yes, that means that d cube r, you have correctly said that it will be 1 over square root of volume. So that xi star psi will have 1 over volume, which will be multiplied with the volume, so as to make the probability a dimensionless quantity. So this thing is automatically built in the way we are defining our PDFs. The PDF does not actually exactly correspond to probability. It gives us probability. Okay, any other question? I mean, I just wanted to remind you those simple things. I guess most of you are aware of it, but it's still good to use it when you are going for the vivas, when you are going for the GRF exams, etc. That make sure that you remember those small things. Questions? So this is another thing about the additional class, that I generally try to highlight few things related with what you might have already done, but I just wanted to emphasize it. I mean, ultimate idea is that your knowledge is incrementing through our classes, and it is not only about that we have to do something more advanced. It is something that it may be very basic, but we'll have to be clear on those basic items. So, okay, guys, I mean, it's 3-4. I won't drag further. If you have questions, please ask it. Otherwise, let's just finish the class. Okay, guys, then see you tomorrow.